One. Okay, so this is the last section before we're going to test. It looks like we're going to finish the notes for this on Monday, practice test on Tuesday, and test next Wednesday, just an FYI. All right, this is the law of cosines, or as I like to call it, the super duper Pythagorean theorem. You'll see why when we get to it, why I call it the super duper Pythagorean theorem. We're also going to learn on Monday a couple of area formulas, only one of them that you have to memorize, though, so to find the area of these triangles. Okay? Now, I am going to derive the law of cosines for you because I always think it's good for y'all to see where these things come from so that you don't just think they fell out of the sky or were imported from France, right, with a heavy tariff. Um, we're going to take this triangle ABC, and I am going to drop a perp from C to make two right triangles. Once I create two right triangles, I can use SOHCAHTOA, right? SOHCAHTOA. And I can also use the Pythagorean theorem. Those only work for right triangles. Yeah, yeah? This is an oblique triangle. What I'm going to do is angle or side C is the entire bottom. Side C is the entire bottom. But I'm going to call this little piece of it, the base of that right triangle, I'm going to call that X, which means this piece here that's left over could be called what in terms of C? If the whole thing is C and I call that piece X, that would be what's left over, which is C minus X, everybody. C minus X. Yeah, everyone good with that? Okay. Now, I'm going to label the altitude H because that's what it is. It's the height. We don't want to label it A for altitude because that's already a side length. I'm going to look at angle A, and I'm going to use cosine. Okay, so remember from SOHCAHTOA, cosine is adjacent over hypotenuse. So cosine of angle A should be the adjacent side, which is what I'm calling X now, over the hypotenuse, which is H. Yeah, yeah? Everyone okay with that? Now let's solve that for X. I'm going to multiply both sides by H, and I get X equals H cosine of A. Now I'm going to stop right there for a second, but I'm going to put an asterisk by that because I might need to come back to that. All right, the next step in the derivation is to actually use the Pythagorean theorem. So let's use the Pythagorean theorem on both of the right triangles. For the left triangle, the Pythagorean theorem, the P theorem as I'm going to call it, is going to be x squared plus h squared equals b squared. Yeah, yeah? X squared plus h squared equals b squared. And then I'm going to move to the left here, maybe put a comma to separate it. And then I'm going to do the Pythagorean theorem for the right triangle on the right-hand side, which is going to be not as fun. It's C minus x squared plus h squared equals a squared. If you object to anything that I'm doing, raise your hand or shout it out, okay? Otherwise, I'm going to assume you're following along with me. These are all things that you can verify for yourself are true, right? Now, ultimately, when I end up with the law of cosines, I want it to be in terms of A, B's, and C's. Whether they're capital letters or lowercase letters, I don't care. I want to express something in terms of the original labels on the triangle. I've introduced two new letters to this so far, right? X and H. So I don't want X's and I don't want H's in my final equation. So now that I've done the Pythagorean theorem, here's what I'm going to notice. I'm going to notice that H squared is actually in both of these equations. Do you see that too? So let's do a substitution. I'm going to solve this first equation for h squared because it's a little bit easier. It's b squared minus x squared. And now I'm going to substitute that in right here for h squared. So I end up with c minus x quantity squared plus b squared minus x squared equals a squared. So the good news is I got rid of my h's. I don't have any h's anymore. The bad news is I still have some x's in here. Well, let's hold off on substituting x for something here because I want to expand out that first term. See, it's c minus x quantity squared. Let's go ahead and expand that out. Y'all remember how to quickly square a binomial? Square, multiply double, square. Square, multiply double, square. Square, multiply double, square. So let's do that. Little c squared is little c squared. You multiply and double and you get minus 2 little c x. And then you square negative x squared, negative x, and you get positive x squared. And then it's still plus b squared minus x squared, and it still equals a squared. Now, if you look closely, you'll notice something good happens in that line. What happens to my x squareds? They cancel. They're gone. Did that take care of my x problem, or do I still have an x somewhere? Oh, I still have an x. Yeah, I still have one x right there. So I need to figure out a way to get rid of x and substitute something in that's in terms of a and b. Well, look what I did over here. Remember this? Remember when we found the cosine of a to be x over h? Oh, I did that wrong. Y'all didn't stop me back then. I actually did I did the cotangent, didn't I? Okay. Good thing we're filming this. I just caught this. Cosine is adjacent, which is x, over hypotenuse. I know why I put h. What letter does hypotenuse start with? H. I was not thinking, and y'all didn't stop me. What is the hypotenuse in that right triangle? What letter is it? It's B. Yeah. Good thing we caught that. Okay. H is actually the opposite side. So I did the cotangent ratio. So let's try that again. Cosine of A is the adjacent x over the hypotenuse B. Solve for x, you get B cosine of A. Okay. Now I can substitute B cosine of A in over here. So I'm going to get C squared minus 2 little c, and then in place of x, I'm going to put B cosine of angle A, and then plus B squared equals A squared. All right, now I'm pretty much there. All I'm going to do is rearrange a couple of things. First of all, I'm going to put little a squared by itself on the left-hand side, and then I'm going to rearrange some of the things on the right-hand side. It becomes b squared plus little c squared minus 2bc cosine of a. And there it is. That is the law of cosines. And you can tell it's the law of cosines because it has cosine in it. Now, I want you to pay attention to the first three letters in this equation, okay? It's a squared plus b squared equals c squared. Where have you seen a squared equals b squared plus c squared before? That's the Pythagorean theorem, right? That is the Pythagorean theorem, where a is the hypotenuse instead of c. The problem with the Pythagorean theorem is it only works for what types of triangles? Right triangles. What we just came up with is a formula, or a theorem, if you will, that works for not just right triangles, because it will work for right triangles, but it also works for oblique triangles, which means it actually works for all triangles. How about that? So now that we have this, because it works for all triangles, including right triangles, we don't really need the Pythagorean theorem anymore, do we? We still hang on to it because it's pretty useful when you're dealing specifically with right triangles. But this replaces the Pythagorean theorem. It's the super duper Pythagorean theorem because it works for all triangles, including right triangles. That's pretty fantastic. Now let's take a look at it, because there's two other versions of this, and you don't have to memorize all three versions. You just have to memorize the pattern. So let's go through and look at the pattern. First of all, I want you to notice that we have little a on the left and big A on the right. Little a and big A are on opposite sides of not only the equation, but also opposite sides of the triangle. That's how I always remember it, right? In a triangle, we have angle A is opposite little a, angle B is opposite little b, angle C is opposite little b. Well, that's how it works in the equation too. Little a is on the opposite side of the equation from big A. Little b is going to be on the opposite side of equation from big B, and little c and big C are going to be on opposite sides of the equation. Now, since I have little a isolated by itself on the left, angle A is on the right. But look what the other two sides are. These are just the other two sides. The other side squared plus the other side squared. It's always minus 2. That's always part of the formula. But notice what we have here. We have B times C. That's just the other two sides not squared. So it's one of the sides squared plus the other side squared minus 2 times the other two sides times the cosine of A. And I was just getting ready to use my calculator and I lost it. Okay. All right, let me show you the other two versions and I'll reload my calculator when I need it. Help me out to see if you can figure out the pattern. If I want to find b, I'm going to isolate b squared by itself. What are the other two sides? A squared plus c squared minus 2ac times the cosine of what angle? B. There it is. So there's another version of it. And yet another version would be c squared equals, what are the other two sides? A squared plus b squared minus 2ab times cosine of angle C. That's the pattern. If you can memorize that pattern, then you don't have to really worry about memorizing any single version. You just know how to use the law of cosines, okay? So we use the a by itself on the left side to find little a. We use the b by itself on the left side to find little b. And we use little c on the left side by itself to find little c, okay? Just remember that whatever little side is by itself, the angle opposite is on the opposite side with the cosine, all right? Okay, if you want to see that written in the box, there it is in the box, all three of them. The law of cosines. Now, to use the law of cosines, we have to know all but one of these variables, which means we need to know a side, an angle, and a side, or we need to know all three sides, in which case we can find an angle. So this is when we use the law of sines. When we have side, angle, side, which I call the easy plug and chug method, as you'll see shortly. It's the plug and chug method. Or side, 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 where we use it to find an angle. Or angles, I should say. All right, now real quickly, let's review. How do we know if I'm giving two sides and an angle that it's the side, angle, side case and not the angle, side, side case? Because both of them have two sides and an angle. And I'm not going to tell you which method to use, right? If it's angle, side, side, that's ambiguous case. Got to use the law of sines. If it's side, angle, side, you're going to use the law of cosines. What do we say about angle, side, side about the letters? We have repeated letters. Good. We have one that repeats. We have a repeated letter. If you have side, angle, side, as you're going to notice, we have all different letters. So you're going to have like little a, little b, and big C, so on and so forth, okay? All letters are different. That's how you can tell if it's side, angle, side versus angle, side, side. And of course, side, side, side is easy to tell because they're all lowercase letters. All right, let's take a look at example 2. Let me reload my calculator real quickly here. All right, get rid of the toolbar and we're in business. Okay, there we go. So here we go. It says solve triangle ABC if little a is 11, little b is 5, and big C is 20. All right, first thing you do is you take inventory. It says to use the law of sines. Let's just get real here. I'm going to change the instructions. On the test on Wednesday, I'm not going to tell you which method to use, okay? I'm just going to say solve. So I notice there's two lowercase letters, so that's two sides, and one angle. Is this angle side side or side angle side? Side angle side. How do we know, Hunter? All different letters. Good. Now, what you want to do is start by drawing a triangle. And you could draw it the same way we did for the ambiguous case. You could do that as your base, here, and here. Now, you don't have to worry about letting that arm on the right-hand side dangle in the midair to see if it reaches, because side angle side will always make a unique triangle. So I'm going to label the base angle 20 degrees, and that's going to be angle C. Therefore, the side opposite is going to be called little c, right? That's how that works. Now you have the option on to which one you want to call the other two sides. It's up to you. I'm going to call, I'll call this angle A, so this becomes little a, which is 11, and I'll call this little b, and that means this b is 5. So it doesn't matter how you label the other two sides and angles, just make sure that the side is opposite the angle. All right, now once you have it drawn, you can clearly tell that it's side angle side, right? It's the included angle, side, which always, always, always makes a unique triangle. So it's not the ambiguous case. All right, so we need to solve. So here's what you're going to tell yourself. I need to find two angles and one side. That's what's left to find, right? There's no way to find the other angle by subtracting from 180, is there? Because that trick only works when we know two angles. So here's what you do when you have side angle side. you have to use the three pieces of information that you're given, which means you have to use angle C. You have to use angle C. So we're going to start by finding the side opposite angle C, which is what? Little c. So which version am I going to use for the law of sines? I'm going to use little c squared. I'm going to isolate it by itself on the left-hand side. Let's go ahead and write out what the rest of it is. It's going to be the other two sides, a squared plus b squared minus 2ab times cosine of angle C. That's the version that we're going to use. All right, now let's plug in. We get c squared equals, a is 11, so that becomes 11 squared. B is 5, so that's 5 squared. Minus 2 times 11 times 5 times cosine of 20 degrees. Now, here's why I call this the easy plug and chug variety. Notice on the right-hand side, we have nothing but numbers, do we? So all we got to do is type it into the calculator and then take the square root of it. Now, make sure you're in degree mode. I had them clear their calculators last time. They were supposed to. So you always check now to make sure you're in degree mode because it defaults to radians. I'm in degree mode now. So now I just type it in, 11 squared, or 121 if you prefer, plus 5 squared, or of course 25, minus 2 times 11 times 5. I don't even bother squaring and multiplying that stuff out because it's a calculator question anyway, times the cosine of 20 degrees. I hit enter, and then you got to be careful. Is that C? No, that's c squared. So all you have to do is take the positive square root, hit second x squared, and then to recall the answer, so you use all the decimals, you hit second negative. Notice it's highlighted in red down there. I don't know if you've ever done that before. Second negative recalls the answer from the previous line with all of its decimals intact. You hit enter, and you get 6.529. And there's no units of length, otherwise I'd put them, feet, inches, miles. And there's little c. So now we want to store this. You want to get in the habit of storing. So we're going to hit stow alpha c and then hit enter. Now it's locked in as c. If you want to come up here and label it, you got 6.529, and you can box it so it stands out in the crowd, so I know where to look when I'm grading it. Now I got to find one of the remaining two angles. So really what this problem turns into now is it turns into a side-side-side problem. I know all three sides, and so we're going to do the same thing we would do if it were a side-side-side problem. I need to use the law of cosines now to find an angle. And it doesn't matter which angle I find. Y'all want to find angle A or angle B? You want a hot dog or a hamburger? It doesn't matter. Angle A or angle B? Angle A? Let's do angle A. It comes first in the alphabet song. Okay? So if I'm going to find angle A, let's do this in a new column over here. If I'm going to find angle A, it has to be on the right-hand side of the equation, which means what goes by itself on the left-hand side? Little a squared. If you want to find angle A, then little a squared goes by itself. So the version that we're going to use then is b squared plus c squared minus 2bc times cosine of angle A. The super duper Pythagorean theorem. Bless you. All right, now let's plug in. I'm going to do A, which is 11, so it's 11 squared, plus B, which is 5 squared. C is stored, so I'm just going to put plus C squared. I don't want to put quotations around it because it kind of clutters it up. Are you okay with me not doing that? When I put a C in my equation, that's a reminder to myself to use the stored value of C. Minus 2 times B, which is 5, times little c, times cosine of angle A. All right. Now pay close attention here because we have to solve for A, which means it's going to require a little bit of algebraic manipulation. But it's going to be the exact same algebraic manipulation each and every time. Is everyone okay with my setup? Did I set it up correctly? All right. What's that? Oh, yeah, duh. Duh. Okay, let's add a mark to the board. Yeah, that's 11 squared equals. Yeah, why did I put plus? Let me add y'all. Y'all are up. Ooh, look at this. There's another. That's 10, so that means that y'all have 5 points bonus on your test on Wednesday. Yeah, it should be an equal sign. Okay, good thing I'm recording this, all my flaws, right? Yeah, so here's the algebra involved. Before I can solve for A, I got to solve for cosine of A. And before I solve for cosine of A, I have to isolate this term. So I need to get the 5 squared across and the c squared across. So this becomes 11 squared minus 5 squared minus c squared. And that's going to equal negative 2 times 5. You can call it negative 10 if you want. I don't care. Times c times cosine of A. All right, now that I've got the cosine term isolated, I need to solve for cosine of A. So I need to divide both sides by negative 2 5c. So this becomes 11 squared minus 5 squared minus c squared all over the coefficient of cosine of A, which is negative 2 times 5 times c. Now that equals cosine of A. The last thing I need to do is solve for A by doing what to both sides? How do I uncosine something? Inverse cosine. Now I'm going to flip both sides. So I get angle A ends up being the inverse cosine of 11 squared minus 5 squared minus c squared all over negative 2 times 5 times c. And that's about the hardest the law of cosine gets. If you could do that algebra, you'll eventually hopefully be able to do it in one step. Subtract the constants, divide through by the coefficient, and stick an inverse cosine in front of it. Now all we got to do is go to the calculator. We're in degree mode, so we hit second cosine, alpha x, 11 squared, or 121, minus 5 squared, or 25, minus alpha c squared, all over negative 2 times 5 times alpha c. We're doing it on the calculator, so I don't even bother calling the denominator negative 10c. You're certainly welcome to simplify if you want, but the calculator will do it. So we hit enter, and look at this. We get angle A is 144.816 if you truncate, 817 if you round degrees. I'm going to box that so it stands out in the crowd. Now, an angle of 144 means it's what type of angle? It's obtuse, isn't it? Do I have it drawn as an obtuse angle in my triangle? Nope. Is that okay? Yes. Yes, because your triangle is only there to help you orient yourself to the sides and the angles. It doesn't have to be drawn to scale. All right? When you want to draw it to scale is when it's the law of sines in the ambiguous case, so you can kind of get a feel for if the other side is long enough to reach. But in this case, it's going to make a unique triangle. Just draw something, okay? All right, so now I have this as 144 point something. All I need to do is find the other angle. Let's store this as A, by the way. Store this, stow alpha A. Boom. I'm going to write store that. Get in the habit of always storing your values. Now that I have two angles, can I find the third by subtracting the sum from 180? Yes. If you'd like, you can also use the law of cosines again to find the other angle, but I'm not going to. So here's what I know. I know that 20 degrees plus quotation A plus B equals 180 degrees. So that means B must equal, now we go to the calculator, it's going to be 180 minus 20 minus alpha A, enter, and you get 15.183 degrees. Did we solve the triangle? Yeah. Yep. We did. We solved the triangle. So we used the law of cosines once to find the side. That was the plug and chug variety, remembering to take the square root. And then we chose one of the remaining two angles. It didn't matter which. We set it up. We did some algebra, and we solved for the angle. We got the second angle. And then once we had the second angle, we subtract the sum from 180 to get the third. That's the law of cosines. That's it. That's as hard as the law of cosines gets. There's no ambiguous case, although you can use the law of cosines to do the ambiguous case. It is possible. You would end up solving a quadratic equation, and the quadratic would tell you if there's 2, 1, or 0 solutions. That's how it was taught to me back in high school, but I think it's easier just to do what we did yesterday on the quiz and then use the law of sines for the ambiguous case. So I'm not going to teach you the ambiguous case with the law of cosines. All right, any questions on example 2? Side angle side and side side side. That's it. Law of cosines. Now example 3 we get to skip because it's the exact same question. This is the same question. The only difference is instead of using the law of cosines to find the angle, I have you use the law of sines, but you have to do so carefully. And I don't even want to go that route. I want you just to use the law of cosines to find that second angle. All right? It's so, oops, same question. There's not two there. Same question. All right, so let's go to example 4. And again, we're going to disregard that. I'm not even going to teach you the law of sines to find the angles, because if you do, you have to find the small. The whole thing is you got to find the smaller angle first, because remember, when you take the inverse sine of something, it gives you an acute angle. It's not going to give you the obtuse angle. So if you tried to find the obtuse angle first, it wouldn't give you the right answer. So let's just stay away from that and use the law of cosines, because remember, the PVR for cosine, arc cosine, is 1 and 2. So if it's obtuse, it'll give it to you. All right, so on to example 4. Here we go. Solve triangle ABC if little a is 9, little b is 7, and little c is 5. Well, those are all 3 sides, aren't they? That's side, side, side. Now, here's the thing about side, side, side. It may make one triangle. So it's not the ambiguous case where we can get 0, 1, or 2 triangles. If there's going to be a triangle, there's only going to be one triangle. Okay? Here's the big if the triangle inequality holds. So let me review you on what the triangle inequality is. The triangle inequality basically says the sum of any 2 sides of a triangle has to be strictly larger than the third. So A plus B has to be greater than C, A plus C has to be greater than B, and B plus C has to be greater than A. If any one of those equalities does not hold, then the 3 sides of the triangle do not join up together to make a triangle. Now, you don't have to test all 3. Here's all you have to do. Add the 2 smallest sides, and then look to see if it's greater than the largest side. If it holds for the sum of the 2 smallest sides, then it's going to hold for the others. Okay? So all you got to do is check the 2 smallest sides. This could be a big time saver, because I might give you 3 sides on a test and they don't make a triangle. Okay? Let's check it out over here. My 2 smallest sides are 7 and 5. What's 7 plus 5? That equals 12. Is 12 greater than 9? The third side? Yes. So this makes a triangle. This passes the triangle inequality. Okay? Good. If that had been like 7 plus 7 and 1, if A were 9 and B were 7 and C were 1, now 7 plus 1 would be 8. That's not bigger than 9. That wouldn't make a triangle. Okay? So check the triangle inequality first for side, side, side. All right, now that I know it makes a triangle, let's go ahead and just draw a generic triangle. Here's A, here's B, here's C, here's little a, which is 9, here's little b, which is 7, here's little c, which is 5. So again, it doesn't matter where you draw the A, B, and C. The only time it's important that you draw it the same way is when it's the ambiguous case. Make sure your angle's in the bottom left. Okay, so I got side, side, side. This is another call for the law of cosines. Now, here we go. The law of cosines doesn't matter which angle you find first. You don't have to find the smallest side. Which angle would be the smallest, by the way, if we were interested in finding the smallest angle? C, right? Because there's also a property for triangles that says opposite the smallest size is the smallest angle, and opposite the largest side is the largest angle. But the law of cosines doesn't care. You can use the law of cosines with reckless abandon. So just pick one of the angles. You want to find A, B, or C. You want hot dog, hamburger, or pizza? Let's find C first. Okay. If I'm going to find angle C, then what has to go by itself on the left? Little c squared. Good. So we're going to do little c squared equals a squared plus b squared minus 2. Don't forget the minus 2. A times b times cosine of angle C. That's the version we're going to use. So we plug in and we get 5 squared equals 9 squared plus 7 squared minus 2 times 9 times 7 times cosine of angle C. Now, is it okay if you call 5 squared 25 and 9 squared 81? That's fine. I don't care. Do as much mental math as you want, but don't mess up, okay? Now, we're going to do the algebra in one step. If you need to do it incrementally, like we did up here on example 2, to solve for the angle, you can still do it incrementally. But you're going to be doing this so often that you're going to get used to it. We're going to end up, and I'm going to leave a little space on the left, we're going to end up with 5 squared minus 9 squared minus 7 squared. That's going to become the left side. And then we're going to divide through by negative 2 times 9 times 7, and that would equal cosine of c. And then we end up taking the inverse cosine of both sides, so that's what we end up with, and that equals c. You should be able to, with a little practice, be able to go straight to that line right there, because it's the exact same algebra every single time. Okay, now we go to the calculator, the Medora, the Explorer, and we go second cosine alpha x, and I'm just going to type in 25 minus 81 minus 49. I hope you're impressed that I know my perfect squares. But here I'm just going to do minus 2 times 9 times 7. I don't care what that's equal to. I'll let the calculator tell me. I was just trying to save keystrokes. And it didn't save any keystrokes in the top. 25 is 2 keystrokes, 5 squared is 2 keystrokes, so it didn't really matter. But I hit enter, and I get 33.557 degrees. Make sure you put the degreble. And then what are we going to do before we move on? Store it. Store it as alpha c. Boom, got it. All right, I know one of the angles. It's 33.557. Good. If you want to label the triangle, you can. I would prefer you just box it so it stands out in the crowd. All right, I need to find another angle, don't I? I need to find another angle. So A and B are both left. Which one do you want to use next? It doesn't matter. A, okay. So we're going to sing the same verse or the second verse to the same song. If I'm going to find angle A, I'm going to do A squared equals B squared plus C squared minus 2BC cosine of angle A. And now I'll plug in what I know. I get 9 squared equals 5 squared plus 7 squared minus 2 times 5 times 7 times cosine of angle A. And then once again, we're going to solve for angle A in one fell swoop. So we're going to end up with 9 squared minus 5 squared minus 7 squared all over negative 2 times 5 times 7. And then we take the inverse cosine of both sides, and we end up with that equaling A. It's the same math every time, so you'll get used to it. Now we just type it in, second cosine, alpha x, 81 minus 5 squared minus 7 squared, whatever. On the bottom, minus 2 times 5 times 7. Double check, triple check. It looks good to me. Hit enter, and you get A equals 95.739 degrees. And again, I'm going to box it, and then I'm going to store it. Store it as alpha A. Boom. Okay, now I'm home free, right? Because now I know 2 of the angles. So I know angle B is equal to 180 minus A minus C. If you want to write that out, that's fine too. I just need to see what you're doing. You always have to indicate your method. So if you put 180 minus A minus C, I know exactly what you're doing. So B equals 180. Oops, I forgot the 1. 180 minus alpha A minus alpha C. And you get 50.703. Make sure you put degrees. And we're done, so there's no need to store that. And there it is. How hard is the law of cosines? It's easy, right? The hardest part is the algebra and solving for the angle, but you do that once or twice and you get it down in one step. It's a piece of cake, all right? So that's the side, side, side. You only use the law of cosines for side, angle, side, and side, side, side. We've already seen both of them in action. So what else is there to do? Let's look at an application, huh? How about that? An application? Example 5. A tunnel is to be built through a mountain. Yeah, right, like that's possible. To determine the approximate length of the tunnel, an ambitious math student, that could be you, right? With a homemade sextant attached to a transit, takes measurements from a fixed point, as shown in the figure. Use the student's data to determine the length of the tunnel. Okay, so he's standing right here at point C, and we want to figure out little c. That's the length of the tunnel through the mountain. He takes a reading to point A on the left-hand side to be 388. That's what we're going to call little b. And then he measures the angle, which to be 82.4, to the other side of the tunnel or mountain, which is 212, which we're going to call little a because it's opposite side A. I just want to find little c. Now, what method are we going to use? Law of sines or law of cosines to do that? We have side, angle, side, right? See that? It's the included angle, side, angle, side. Side, angle, side is always the law of cosines, LOC, law of cosines. And it's the plug and chug variety. It's the easy variety. So here we go. We're going to have c squared equals a squared plus b squared minus 2ab times cosine of angle c. Let's plug in. C squared is going to equal a, which is 212 squared, plus b, which is 388 squared, minus 2 times 212 times 388 times cosine of the included angle, which is 82.4 degrees. All you have to remember to do for the plug and chug variety is to take the square root of the number at the end. I'm not going to make you solve for c and put the square root over that whole thing. If you want to, you can. Just put c equals and remember to take the square root of your final answer. Don't forget that. Okay, so here we go. 212 squared plus 388 squared minus 2 times 212 times 388 times cosine of 82.4. Close parentheses, hit enter. Is that the length of the tunnel? Nope, I got to hit second x squared and then second negative. That recalls the answer. And now you get 416.809 or 810, and then we put units, feet. Always put units on your final answer, whether they're degree bubbles or feet, inches, miles, whatever. And we are done. That's all we're going to do today, 1 through 5. Any questions on the law of cosines? That's not so bad, huh? Maybe the hardest part is remembering the formula, but I think you got that down just working it today. Law of cosines is pretty cool, okay? Together, the law of sines and the law of cosines make a powerful duo for solving any triangle, okay? Let me do one more thing. This is just kind of a little note here. Let's say that I have this as angle C, and let's say it's a right angle. And this is A and this is B. This would be little c, this would be little a, this is little b. I want to show you real quickly that the law of cosines also works for a right triangle. Okay? Let's say we want to find little c. So little c squared equals little a squared plus little b squared minus 2ab times cosine of angle c. Now the Pythagorean theorem, as you remember it, is just the first part, right? C squared equals a squared plus b squared. So how are we going to get rid of this whole extra part right here? Well, because of that. What is the angle measure at C? 90 degrees. And what is cosine of 90 degrees? It's 0, right? It's the same as cosine of pi halves. Cosine of 90 degrees is 0. So what happens to this whole little piece right here? It goes away, and we're left with c squared equals a squared plus b squared, which is the Pythagorean theorem. So does the law of cosines work for all triangles? It does. Do you really need the Pythagorean theorem anymore then? Not really. Not really. It's fun to keep because when you have a right triangle, you don't have to worry about getting rid of that second piece or that third piece all the time. But it works for all triangles. Okay, now we're done. Any comments or questions? Like, I like pizza. No? Okay, we're done.